For the problem 1, we are given we are given xt, which is a real stochastic process, and it is wide sense stationary. So we have its autocorrelation of x is only depend on tau, where tau is the difference of the autocorrelation of the two x. So we have the autocorrelation equals to the expectation of xt plus tau times xt. And since xt is real, so xt plus tau is also real. So this term, the product of them are also real. So the autocorrelation is also real. And to prove that the autocorrelation is an even function, we write it, we just reverse the order of these two terms. And then we get it equals to the expectation of xt plus x times xt plus tau. And it is equals to the autocorrelation with t plus tau. And if we minus t plus tau from t, we get it is minus tau. So we can see that from this equation, we can see that the autocorrelation of xt is even and real. For this is for problem A, and for problem B, we need to prove that the spectral density is even and non-negative. And first of all, we show the spectral density is even. And to show that, we just plug in the formula of the spectral density. It is equals to the integral of from minus infinity to infinity of the autocorrelation, the Fourier transform of the autocorrelation. So it's in this formula. And we just expand this term, and we got it is equals to the autocorrelation times cosine omega tau minus j times, here is the same, times sine omega tau, and integral from minus infinity to infinity. And since this term, this function, it is even, it is odd, so the multiplication of them is an odd function. So the integral of this term add up to 0. And since this is even function, this is also even function. So the integral, so the product of them is even function. So we can decompose it into, rewrite it into the 2 times of integral from 0 to infinity. And the inner term is r tau cosine omega tau integral of d tau. And since it is an even function, we can rewrite omega tau to be minus omega tau, and the result will not change. So given that it is equal to minus omega tau, and this term is equals to spectral sum given the minus omega as the parameter. So in this one, here we have complete proof that the spectral density is even. And let me make it smaller. To show that the spectral density is non-negative, we have let's consider H omega as an ideal single frequency pass filter. So H omega, let it to be this formula, and it is a filter. It only will pass the signal at omega 0. And we have the expectation of yt, which is xt after the filter, and we take the absolute value. It is greater than 0, and it is equals to, based on the formula, it equals to the integral from minus infinity to infinity, and it integrals from h omega power of 2 times the spectral sum of x, and since it is x past the filter h, and we get y, so the expectation of y is equals to this formula, this formula, and we get that it is greater than 0. I don't know, and since this term is greater than 0 and the whole term is greater than 0, so the only possibility is that Sx, the spectral sum, is also greater than 0. So we complete the proof that the spectral sum is non-negative and even. This is for the problem